morning, everyone. I'm here on behalf of the International Space University, where I did the Space Studies program this summer. ISU organizes a summer session in which teams do a project. The project that I'm presenting here is Project SolarMax, which was a project about, what does it says here, about space weather and spacecraft protection. So what I'm going to take you through is really simple. Three very basic questions. You can see here, what is the problem with space weather? Why should we care about space weather, and what can we do about it? So to go to the first one, what is the problem? The problem is really simple. Space weather destroys stuff. And in this presentation, I will take you a little through what that means and why that is a problem. So if we look at solar physics, the sun goes through an 11-year activity cycle, from solar minimum to solar maximum, back to solar minimum. In a way, it's a 22-year cycle, because as most of us here know, that during solar maximum, the polarity of the sun, of the solar magnetic field flips, going through another 11-year cycle when it flips again, taking 22 years to go back to the original position. During this solar cycle, all kinds of activities in the sun happen. Whether or not this is related to things like solar flares and coronal mass ejections is still being subject of research. The message of this slide is really that we know a lot about heliophysics, we know a lot about the behavior of the sun, but we don't know everything, and there are still many aspects of the sun that we do not understand, where further research is required. What we do know is that coronal mass ejections happen, that solar flares happen, and these events throw large quantities of high energy particles into the solar system in all directions, including towards Earth. And when these charged particles interact with the Earth's magnetic field, first of all, we are protected that way, as we all know. It causes aurora borealis by the effect of the charged particles in the atmosphere of the Earth. But when there's really massive events, things happen to the size of the Earth's magnetic field, and charged particles may penetrate into areas of the Earth and cause problems. So there are possible impacts on humanity, and these impacts we don't see very often. These are very low frequency events, but the impact can be really high, and in the past history we have seen a few examples of that. But just a few examples of what happens due to solar weather is satellites stop functioning, there's issues with the power grid, we have certain critical services that we learned to depend on very heavily in modern society that we lose, and ultimately there is a very small chance of major global crisis. So why should we care about this? Well, you've seen the possible effects. Again, very low frequency, we don't know when it will happen, we don't even know if it will happen, but in case it does happen, the impact is really, really high on society. And as J.M. Barrie said over 100 years ago, everything has happened before and everything will happen again. So, a very recent, well not recent, but one of the most recent examples of a very big space weather event took place in 1859. And when I learned about the Carrington event a little while ago, I thought this was common knowledge. This had been common knowledge for a long time. In fact, the real impact, the true scale of the Carrington event has only been known since 2005, when a NASA researcher, Dr. James Green, started to dig into the archives of this astronomer, Mr. Carrington, and found out what really happened in 1859. And he connected the effects that were reported in newspapers, aurora borealis at very low altitudes, telegraph lines showing problems, all kinds of things that happened on the planet could be related to this solar event, which was very well described by Mr. Carrington in 1859. The strongest geomagnetic storm ever recorded at this moment. But that was not the last time that it happened. In March of 1989, and most of us here will remember, a large solar storm hit Earth, causing problems in the eastern regions of Canada. And the knock-on effect that was created by the geomagnetic storm in the power grid in Canada had a big effect on a very large region, losing power for several days in certain cases. The interesting fact is as soon as you start investigating the numbers, and again, investigating these knock-on effects in the sense of economic impact is very difficult, but the last estimate is the damage cost was in between $4 and $10 billion. Again, that wasn't the last one. Maybe a little bit less known, in 2003, a strong solar storm hit Earth, causing the so-called Halloween effect, happened during Halloween. And again in North America, the New York area suffered from a blackout, again over a day, affecting millions of people, where the associated damage, because it's a highly populated area, was estimated at even higher than the Quebec event. What we also noticed in 2003 is that certain spacecraft either were lost completely or degraded in functionality quite significantly from the effects of these charged particles. So as I said, these examples are very low frequency, so they don't happen very often, they happen infrequently, but the impact is really high. In this case, the impact was relatively local, the impact was a couple of days. That's okay, but they happen all the time. The thing is, we cannot predict these CMEs and these solar storms at the moment. They're not necessarily linked to this 11-year solar cycle, although there is some relation. When the solar activity is high, the chance of solar flares is higher, but there's not a statistical effect, and in fact the Carrington event happened during a solar minimum. So what if a Carrington level event would happen today? Well, today the world depends much more on electricity, on power grids, on connected grids than in 1859, of course. I mean, lots of things have happened, and our society is heavily dependent on these infrastructures today. The same with the space infrastructure. Today, like never before, we rely on the space infrastructure for navigation, for communication, for all kinds of services that we deem necessary for modern society to function. If a Carrington event would hit Earth today, we may lose much of that infrastructure for days, for weeks, or even for months. Repairing the power grid, the electricity grid, is not a straightforward thing. We do not have spare parts in stock to repair these connection points in the power grid. The same with satellites. A satellite cannot be replaced in a couple of days. Those things take time. It's not impossible, but it takes time, and we may have large problems. And now it becomes a little bit more philosophical, but what if Carrington event is not the maximum scale of a solar event? What if Carrington was just a medium level event in a way? What if the sun is capable of doing much more damage? Well, in that case, the implications may be much bigger and are beyond imagination in current level of knowledge. So what can we do about it? Well, in the project team at ISU, we came up with 3 different things. First of all, it is important that the world knows about this, that the general public is aware of this potential danger. Again, the danger is a low frequency but high impact danger. We should not worry immediately, no reason for panic, but there is a risk involved here, and we just don't know enough to assess the size of the risk. We need to protect our terrestrial infrastructure, our power grids, as I mentioned, but also we need to protect our spacecraft. So since this talk is about spacecraft protection, a few things about it. There's much more in the paper that is behind this. But there's a few things in the spacecraft protection area that I'd like to highlight that we need more research on. First of all, we need to understand solar physics and space weather a lot better. Then we need to prepare our satellites. Our satellites at the moment, the way they are designed, are very vulnerable. And we need to make them less vulnerable. There are ways to do it. In the military satellite world, there's examples of how we can harden our satellites, the electronics on board satellites, for space weather events. We need to rethink human spacecraft design. Maybe redesign human spacecraft, missions to Mars, 2018 for example. Simply by redesigning the spacecraft interior, we're able to protect astronauts on board the spacecraft in case these events hit. And last but not least, we need to improve our space weather detection and forecasting network. Spacecraft like SOHO, like SDO, are bound to be replaced at some point, and we need to make sure that we have that capability in space to detect these issues. So, again, in the paper there's much more about this. 36 people worked on this. I had to stick to about 10 minutes, which I think I just reached, so I'd be open for any questions. Thank you very much.